All right, thank you, Mohammed. So as he said, I was going to talk about a typical load test done on a precast concrete tub stadium riser. And then as an extra bonus, I'm hoping to talk about a bond test of a number 20 bar that we did on a different project. So the first project involves a stadium modernization where they expanded the north end zone of a particular collegiate stadium. They're expanding it for box seats, increased capacity, as well as some concessions. And when they were installing the cantilever precast tub risers in this region, they noticed some cracking shortly after the erection. This is looking at a cross-section through that new area of the stadium. And you can see that there's a lot of steel structure and steel trusses, but what we're looking at is at this mezzanine level where we have the steel truss cantilevering beyond the frame and then the steel tubs on top of it. So zooming even further into it, you can see that the steel truss cantilevers out, and then we're looking at this particular concrete tub riser. And you can kind of see it in the next picture that it also cantilevers beyond the steel truss. And so it's a pretty unique condition of a cantilever upon a cantilever, and has a couple different support conditions. So at the ends, it's supported on some bearing pads right at the tip of the truss, but then it also has some embedded connections that provide some moment and restraint for that cantilevering portion that we're seeing here. The typical panel or typical riser that we're looking at is about 28 feet wide and 7.5 feet wide. And the cantilevering portion is that 4 feet that we're showing there on the screen. Looking at our support conditions, the blue corresponds to that bearing pad, and then the red boxes correspond to where those embedded anchors are located. Kind of a unique question that first develops when looking at this is which direction actually controls. Is it the longitudinal direction between the blue supports, or is it that transverse direction where you're getting the cantilever? And if you just look at slenderness, you actually get pretty similar results. So you have a slenderness ratio of about 14 for the longitudinal direction and 17 for that transverse direction. So pretty interesting comparison between the two, and it's not immediately obvious which control. But the distress that created this question of the capacity is the cracking that's observed at the ends. And so we can show this as a crack map on the typical plan. And it's right where those, it's in the non-cantilever portion of the support. So it's where you have to resist the torsion and the cantilevering moment as well. And it's a condition that exists at all of those tubs across the width of that north end zone. So it has some response that's longitudinal, but it also is being dominated seemingly by a torsional and a cantilevering transverse direction. So the precaster, along with the engineer of record, they talked about what they could do, and they wanted to retrofit the specimen and then perform a load test. So that required shoring the riser and then putting in a steel frame on the backside to help resist that torsion and cantilever response. After they put this in, they just removed the shoring slightly so that we could then perform the load test. So it was there for, but it wasn't engaged. And then it involved loading the front side, the cantilever portion, with water in these industrial totes. The picture of that retrofit is seen here. So it's that steel frame that connects the front side to the back side of the riser. They wanted to do the load test in accordance with 318. We've talked about all those conditions, but essentially we had a test load magnitude of 150 PSF, and that was equivalent to 30 inches of water in these industrial totes. As Brian and Keith have both talked about, we were measuring deflection, and so the deflection measurements were on the front side, and we loaded it in 4 increments and then waited 24 hours to see how the structure would respond. In addition to doing the deflection measurements, we also measured crack widths. So it wasn't a criteria, but we wanted to understand if something was happening during the loading process. Just looking at our instrumentation, we have the 3 red boxes that correspond to the front side, the tip of the cantilever. So we had instrumentation there, but we also had instrumentation where the supports are. So on the left side, that's right where our steel truss is. And then just to understand if there was any longitudinal behavior, we also had it at mid-span. So that's the second blue box. So starting to look at how the structure responded to the load at our first load increment, we actually did get a response from the truss, 0.02 inches, but it was essentially the same at the mid-span along that same line. So really wasn't seeing any longitudinal response from the gauges, but you did see a response along the front side of about 0.07 inches. Moving to the next load increment, essentially doubled for all these measurements. And then if I skip to fully loaded, we see a little bit more than doubling, but kind of within the accuracy of the measuring devices. So 0.027 inches of total deflections at the tip versus 0.1 inches at the trusses. And this is what it looked like in the fully loaded position with 30 inches in each of those totes. So the predicted truss deflection from the design engineer was 0.08 inches, which is pretty close to what we measured. And then the relative tub deflection at the cantilever was between 0.15 and 0.2. So, after that first fully loaded, I was thinking we're pretty close. We're in good response from the structure. It's behaving predictively. But once we went to the 24-hour hold, we saw some increases in that deflection. So we got anywhere between 15 and 30% of increase in deflection. Once we unloaded it, we saw residual deflection in each of the locations. So it dropped, some of those dropped by half, but we still have some residual. Waiting an additional 24 hours, we got some equalization in each of the sensors so that we're about 0.03 of residual at the truss location and 0.15 inches along the tip. But that was a 10 to 60% reduction, or absolute change of 0 to 0.06 inches over that 24-hour period, just waiting an additional 24 hours. Looking at that graphically, these are the two responses at the support condition. You see that during the loading procedure, it actually was very linear. We got some slight increase from that 24-hour hold, and then they recovered a little bit. Looking at the ones at the edge of the cantilever, they also behave very linearly during the loading process. And they also extended due to the creep and the microcracking that Brian was talking about earlier after that 24-hour hold. But they do all have residual deflection. You can take out the truss deflection from each of those measurements, and this is the relative response at the cantilever, so taking out any of the truss. And it also has a very linear behavior during the loading process. So looking at applying these measurements to the acceptance criteria, we had a little bit over 0.2 inches of maximum deflection and a residual deflection between 0.08 and 0.12. Looking at our crack widths, we were able to measure the crack width right at the edge, and we had two locations that we could track with the loading. So they started prior to the test at 25 mils, grew about 10 mils to 35 at 100% loading, and then dropped a little bit after final unloading. So we still had an additional residual of 5 mils from the loading process, and that was consistent on the other side as well of the riser. So started 15 and 35, jumped up to 25 to 45, and then dropped again 5 mil of additional crack width. So comparing it to the maximum deflection, you have to meet either one of these to pass the test using the crazy L squared over 20,000 that Keith was talking about. Has a maximum deflection of 0.08, but our maximum deflection was a lot larger, so that we couldn't rely upon that to pass the test. Moving into the residual deflection, dividing our previous deflections by 4, we saw that the criteria was 0.05 to 0.06, but our actual deflections were much larger than that. So we actually failed both sets of criteria for this, and it didn't pass. And I thought that was interesting because initially the test was very linear and followed the response, the expected behavior. And I'm putting it out there as a case study just to kind of create some conversation about this, whether it's the fact that it was a cantilever behavior that dominated it, and those are much harder to actually meet a load test, or as compared to, say, the continuous behavior that we were talking about earlier. So I'm sure when Mohammed gets up, if you have anything that can contribute that you've done a cantilever load test, he would love to add it to the database. But it created a situation where the precaster, in that they didn't know what to do next. Could they retest it and see if they could get a different residual? Could they perform a cyclic test and understand how the behavior, when is it starting to deviate from linearity? Should there be a more understanding the analysis a little bit more, or some other retrofit option? In the end, they chose a different retrofit option, and based off their discussions with the engineer of record, I guess they didn't need to do additional load testing because of the specific retrofit. But it's just an interesting case study for discussion purposes, I would say. One thing that did influence the results is the fact that putting the string potentiometer, we had to go 20 feet up in the air. And so it's going to be affected by the thermal swings day to day. And when you take into account that, it's only a 0.02 inches of expansion in the sensor. So it was well below what we would have expected, but it's something to consider for any load test that you perform, calculating that ambient temperature and correcting for the results. So the next project I want to talk about is a Corpus Christi project. It's the replacement of their existing harbor bridge, which is what you see on the left, with this new harbor bridge that you see on the right. So the project is a cable stay bridge that is going to have the longest main span in the U.S. after it's done, supposedly, over 1,600 feet long. And because of where it's located in Corpus Christi, it required some pretty significant footings due to the soil conditions there. The design team wanted to use some number 20 bars in their footings to alleviate congestion in the footings. And so a number 20 bar, if you're not aware, is 2.5 inches in diameter. And if they even wanted to go beyond just using a number 20 to using grade 75, so a single bar has a yield capacity of 368 kips. So pretty significant loads. This particular bar was supplied by Williams, so it's threaded, and they had terminators that could thread onto the ends. Just for comparison, a number 20 is the equivalent of 16 number 5s. So provides a significant amount of reduction in the amount of steel that you have to place. So for the particular test of confirming the development length for this, 2 beams were fabricated. The beams were 6 feet deep by 4 feet wide and just over 15.5 feet long. And the calculation by the design team was a development length of 4'8". So that's the test that we're trying to verify, is whether this 14 or 4'8" is appropriate. So to test that, a PVC tube was placed in the middle from the end of the terminator of the bar. So in each of those 2 number 20s that you see in cross section, there were some additional bars placed in the specimen. So there was a number 5 bar that was grade 100. This was put there by the contractor to verify that the number 20 bar got to its yield strength. They also had some 14 number 5s around the perimeter. This was to replicate the additional reinforcement in the footing. And then they had some stirrups there to preclude shear failure during the test. In addition, they also had some hairpins that are shown here. But the test was to put 2 specimens backside, one on top of the other, and then test them at the same time. So you're essentially squeezing the 2 specimens together and trying to get to the yield strength. And so that means that the number 20s are in the bottom of the top beam and on the top of the bottom beam. The instrumentation plan was to install strain gauges. The original request was to install a vibrating wire gauge on the number 5 bar to then infer what the number 20 bar was doing. We later convinced them that if you want to understand what the strain of the number 20 bar, you should just measure it directly. And so we put some strain gauges on the number 20 bar to measure that. We also installed some external strain gauges. Did that by using LVDTs over a fixed length. And that length was to correspond to the PVC tube. And that way we could, if we lost any of our internal strain gauges, we would have a backup. We also measured strain just to understand if there was any slip at the ends, and then measured deflection and pressure in our loading equipment. The acceptance criteria is different from what we were talking about earlier. We just wanted to confirm that it could reach 75 KSI. So a load deflection curve for an individual bar was performed, and the strain that corresponded to 75 KSI was 2,800 microstrain. So we're just trying to test, can we get to 2,800? And then we didn't want any slip above 0.04 inches and no other evidence cracks along the bond of the number 20. Because of the load that we were placing on the beam, we had a 50-foot buffer to keep everybody away. So we're talking 1.2 to 1.5 million pounds expected for our load specimen. So looking at the response of our internal strain gauges at the number 20 bars, we initially started loading and got very little response out of either side of the beam. And then we heard this loud bang. And once we heard that loud bang, we saw a huge increase in the bottom beam response. And that loud bang, after it frightened everybody, we realized, hey, there's a crack there. And it was just a loud energy release for how much load we were talking about. So we continued loading, and we heard another loud bang. And we started looking at the response of the top beam and being confused by it, being, what's going on? Why is it jumping around all over the place? So we started looking at the external strain gauge at that location and saw a lot more consistent behavior. And that's when we decided that the top beam internal strain gauges were just no good. They were malfunctioned. And so we started relying upon the external strain gauge at the top beam. And you can see in the bottom beam that external strain gauge is actually tracking very well with the internal strain gauges. So we continued loading until we got up to a minimum of 2,800 microstrain in each of the specimens. Unloaded, and you can see that there is some residual strain that's still there from the cracks that formed. But just comparing the external strain gauges to each other, they actually track each other very well in terms of their maximum response. They can both get up to a little over 3,000 microstrain. The big difference between them is where they have that big jump just to correspond to the different crack. Looking at the response at the ends of looking at slip response at the ends, they actually are well below the 0.04 threshold for this test. And then looking at the specimen, the beam specimens after everything's unloaded, put a crack comparator up there, measured the crack width, and just doing a rough calculation with the crack comparator to our residual strain, they actually match very closely. So a 40 mil crack in the beam on the left, divide that by the gauge length, and it actually is very close. And we got the same type of response with the other beam as well. So this particular test met the acceptance criteria. So it was a very successful test for the design engineer, and the general contractor allowed them to use this number 20 bar in the beam. And it was kind of interesting for me to, in school they always tell you, well, the steel doesn't really do anything until something cracks. And that's what we found in our response. And that was very interesting and to see in a big load test. Some of the lessons we learned is the need for redundancy, having that external strain gauges saved us in this regard. And that's important because of how expensive a test like this is. And we also had some redundancy in our equipment and actually measuring the right thing. Measuring that number 5 bar didn't do them much good, whereas measuring the number 20 bar directly was the key part. So with that, I'll end my presentation and open it to any questions.